Hey class, Adam Ward here. Yesterday we didn't have time in lecture to get through all of the examples that I had posted, and I wanted to work through one of them, which was following example 4.4 in your textbook. And so this is about what happens if we get superposition of loads, meaning multiple different loads, including time shifts, so they don't all start at the same time. Now, the setup for this problem is provided on the slide here. We've got a Lake Michigan, we've got a background concentration of 3 milligrams per liter. We know that around 1930 we start the widespread application of road salt, and that's increased in an approximately linear fashion. And the difference between pre-1900 and post-1900 associated with population is highlighted here in blue. So we've got a background, we've got a linear loading of road salt, and we've got an exponential loading due to population, and our challenge is going to be to think about what would we want to do to simulate the time series of concentration in Lake Michigan. So a few things that should be going through your head right now. We're interested in the time series, so it's not a steady state problem. You should be thinking, well, I don't have a particular solution for this, but I know something about linear loads, I know something about ramp loads. And at this point, let's also just quickly note for chloride, this is chloride ions, so think Cl minus from chemistry. So they're not going to react in the environment. They're typically conservative, so reaction rate of 0, and they're not going to settle because they're dissolved, so settling velocity of 0. So straight away, we can think that lambda, describing the removals from the system, is only about physical removals or flows out, and you can even go ahead and calculate that if you want to on two values of 0.01 per year. That'll be the last calculation that I do today. I'm going to talk through this conceptually to help you see how to set it up and leave you to do this on your own or follow what Chapra does in terms of actual numerical solutions. So let's think about how we can address this problem. I think it's helpful to start by drawing a picture here. So what I'm drawing on the top right of the slide now is a plot of the loading to Lake Michigan through time. So in the pre-1900 period, we don't actually know what the loading is. We could calculate it if we want to. If you wanted to challenge yourself, you could try and figure out what would be the loading rate for Lake Michigan pre-1900. We didn't get it specified in this problem, but we know that it created 3 milligrams per liter, and we'll assume that the lake was at steady state. So that background load is going to continue. We're told that in 1930 we've got a linear load starting, so I drew that in red. And in 1900 we've got an exponential load, so I'll draw that in purple. So at any given point in time, you can look across this plot and you can see which of these particular solutions am I going to have to add together. So we'll walk through these three different periods. I'll label them 1, 2, and 3 to make sure things are nice and clear. So, all right, top left, pre-1900. All we've got happening is the background loading. We don't know what it is, but we know it yields a concentration of 3. So if we're interested in pre-1900 conditions, our answer is 3 milligrams per liter. Things start to get more interesting as we move to the right. So in segment 2, 1900 to 1930, we've got both our background and our exponential loading. Okay, well, that's not a problem. We can go to our equation sheet. What you can see here is that I've pulled two different pieces together then. The first term here being the background concentration, and the second set of terms being the exponential loading. You'll notice in all of these cases I used the pluses where there was a plus or minus option in the equation sheet because it's an exponentially increasing load. A couple other things to point out to you here. I wanted you to see what I did with the time. So in this problem, we need to keep everything on a uniform basis for time. And so what I've decided to do is treat time, t, as though it's the actual year. And so if I want to know the concentration 5 years after this load began, I would want to know the concentration in 1905. Right? But if I plug in t equals 1905, I want to make sure that what the result is that exponent doesn't have 1,905 years. I want it to be 5 years. So we need to correct for that time to make sure we're keeping everything on the same basis. What we normally do is we assume t equals 0 at the start of our problem. But here, because things are progressing through time, we need to pay a bit more attention. Okay, so you could readily go through and find the values that need to be plugged into this equation, put that into, say, a spreadsheet, and make a plot of concentrations through time. And then as we move to the third period, which is after 1930, we have background load, we have exponentially increasing load, and we have a linearly increasing load. And so once again, I'll pull in the first two terms like we just wrote already, and then what you see me writing along the bottom right now is the particular solution for a linear load, or a ramp load as Chapra calls it. And so to be really clear, these three terms, C naught, the first one, represents the background loading and the concentration due to that. The second term, which I've underlined in purple, is the exponential loading. That's identical in every way to what I wrote in section 2. And then that bottom term is the added linear loading. And once again, note that we've got that time correction in there so that we're correcting it for years since 1930. So if you were going to solve this problem or want to plot this out, for example, you would use equations in section 1 before 1900, in section 2 from 1900 to 1930, and in section 3 for 1930 and onward. And so what will happen then is you've got these three different equations, so your plot would end up segmented into these three pieces, just like we drew the loading up above. Just to try and get our heads around it one last time, if we thought about making a plot of what the concentration should look like, just conceptually what would happen, it should be steady state at 3 prior to 1900. If we then add that exponential load, we'll see an increasing concentration up till 1930. And you'll notice I put that dashed line after 1930. That's to sort of represent the idea that the exponential load doesn't stop. It would continue going past 1930. So if we only had the purple load or the exponential load added, that's the line we would get. But that's not the case. In 1930, we have this new linear contribution of chloride take off, and so that response is additive atop what would have been there with the exponential. So the line that we would expect to see, let me trace that for you all in green just to be explicit about it. Our concentration ought to be steady at 3, then have this exponential response, and then have a steeper response than the exponential would have alone. So that green line is what we would expect as a solution to this problem. So at this point, hopefully you're comfortable with the idea of grabbing these different particular solutions, being able to add them together. You're able to deal with any background concentration that may exist. And this is the first time that we're seeing these things split out in time, so that we're actually generating different solutions for different periods of time where their conditions are simple enough that we can deal with them in our equation set. I hope this helps, and I look forward to seeing you all in class. Thanks, everybody.